Okay, so to end this session, we have a practical demonstration of the IM2D tool, and that's going to be given by Matteo, who is sitting right there. So go ahead.
Hi, everyone. Maybe it's better to see my screen. Okay. I will just thank you for the introduction and the opportunity to present our results. Here I will just show you a few slides to introduce the IM2D demonstrator that we have developed, and then I will pass to a live demo of how it works. So I would like to thank most of all Francesco Benedetto and Claudio Rosati at Applied Materials that did the hard work behind the demonstrator, together with Flaviano and Matthias from Fraunhofer Institute and the PFL, because they give us big support developing the connection through AIDA and Symfony. And also other partners have been involved into the project to develop specific workflow, and we saw it, we will see it later. This is the outline of the talk. I will give you a brief description of the goal of IM2D. Then I will show you the components of the toolbox, the interconnection that we have developed, and its functionalities. Then I will provide you a live demo with an intro to Genestra and the device simulation. If you want to go more into the details of device simulation, I remind you that there is a talk tomorrow by Andrea Padovani. And then I will show you the fluxes, device to material and material to device workflow that can be, for which IM2D can be used. And then some functionalities as database navigation, import and export of crystalline structures, the computation capabilities, and the adaptability of the GUI to the user expertise. Something that Matthias was talking before. So we have already discussed yesterday about device simulation and atomistic simulation. They are two different areas with a lot of connection between them. Usually, if we want to study devices or we want to simulate devices, we can start from experimental data. As Johannes has shown you yesterday, we start from experimental data and we want to get an insight on what's going on. For example, understand if there are defects, which is the effect. Do we know that, can we identify that defects? Or we want to run just simulation to make prediction and to drive the device fabrication or the development. Or maybe we want to make optimization simulations, so to get or understand which is the best set of parameters that give us a certain result in the device characteristics. But all these device simulation, as it is obvious, are based on material parameters, the material that compose the device. And this is the field of atomistic simulation, to understand the materials, characterize them, their electrical, optical, and thermal properties. And we need to, let's say, to bridge the gap between the two areas. There have been a lot of effort in the past. There are some difficulties because usually people even do not speak the same language. Some parameters that are used for device simulation that correspond to parameters of material modeling have different names. So people are even not able to talk in a straight way. So what we want to do is to bridge the gap, and I took this sentence from the proposal of the INTERSECT project. So we aim at the realization of an advanced, industry-driven, interoperable material-to-device simulation box for emerging electronics. So we want to build a tool that is able to make the two areas communicate each other. The goal is to enable a direct communication between material modeling and device modeling based on ontology. And you have seen the importance of ontology and EMO this morning. And then we want to allow also the user for the exploration in both the direction material to device and device to material approach, and enable different users to take advantage of the shared infrastructure, because maybe a device expert or an experimentalist is not aware of what is behind the DFT simulation and cannot perform usually DFT simulation or launch that kind of computation. And it's true often also the vice versa. And we want to bridge these two different worlds so that an experimentalist can have access to the other field and launch simulation even if he do not possess the required knowledge. And finally, we also have identified some turnkey parameters that are, let's say, the most important for device simulation, and we wanted to develop automated workflows in AIDA, using AIDA, so to obtain, let's say, in a kind of data-on-demand model, some parameters that maybe are required for the simulation. These are the key components of IM2D. So we have quantum mechanical codes that are Siesta and Quantum Espresso. We use the AIDA platform for data management and the automation of workflow. We use Symfony for the semantic description and ontology. And then we use also the Optimade API to allow us to communicate with also external databases, not only our local database of AIDA, so that we can have access to a large data set and list of materials. And then we use Genestra for device modeling. What we have developed, in particular at Applied, is the material property browser. Here you see like a sketch. The browser can work both fully integrated into Genestra or in a standalone version. And what we have done is we have defined some properties API that describe the abstract behavior of the browser. So the browser is based on this API, and we have implemented different plugins, some implementation of this API to talk with different services and providers. An example is AIDA or Symfony, our internal material library of Genestra, then Optimade and as a test case also Materials Project. On the other side, for example, AIDA and Symfony, they had to develop some plugins that extend the AIDA API capabilities, or add, in the case of Symfony, add new features or a higher level communication to make this connection. So what's important is that in this way, the property browser operates independently of the chosen implementation, and it adapts to what has been implemented in each plugin. Here is a schema of how it works. It is similar to what Matthias has shown you before. So we have the material property browser. We can access to it either directly or through Genestra if you are a Genestra user, because I remind you that Genestra is a commercial software, so you need the license, and in case you do not have access to Genestra and to its functionalities, you can still use the IM2D toolbox. As I said, it's fully integrated into Genestra, but it can communicate also with external material databases based on the Optimade API, and it can communicate with the IM2D interoperable hub that has been developed by Flaviano and Matthias. So, and there is where you have your local database that is managed by AIDA, and the quantum mechanical codes, Quantum Espresso and Siesta. On top of this, you have not only AIDA, but a plugin that has been developed by the PFL, that is AIDA Post, that implements this API. And you can communicate either directly to AIDA or passing through Symfony. This is a higher level of the communication that, as I will show you later, introduce you some new functionalities, not only the semantic description. Here is a list of the functionalities that have been implemented so far or are under development. So we have the structure search and properties inspection of the databases. Then we can import or export structure in the CIF format. We have implemented some workflows as the computation of the bandgap, the structure, effective mass, total energy, the electric constant, and defect formation energy. Then there are other workflows that are ongoing, as the nudged elastic band, computation of the mobility or thermal conductivity, work function, but the list of the desired quantity can be much, much longer. We will see what we will be able to obtain by the end of the project. And finally, we have developed a computation panel that is dynamic and adapt. I show you a specific list of parameters that are adapt to the properties that you want to compute in through your workflow and the user expertise. And with this, I will go to the live demo. I hope the services are still running. Okay, this is Genestra. In Genestra, you can create a project. I have created this one for our demo. In a project, you can create new devices and simulate their characteristics. I can create a new device from a template. We have several templates. For example, I can create a MOSFET, a cylindrical capacitor. I can create a FinFET, and so on. Okay. So you can, or if you have your own structure that you can maybe create using a CAD, then you can import it in the VTK format. I've already built a structure for this demonstration. It's a cylindrical transistor. Oh, it's a bit slow today. Sorry. Okay, here it is. The structure is identified not only by the geometrical properties that you can modify here, for example, the thickness of a layer, but it is identified by electrode that define the boundary condition of your simulation. So we have source and drain electrode that are treated here as ideal contact. Then we have the gate that is a metal, and as you can see, it is described by some physical properties as its work function. In this case, I've chosen the tin. Then we have the regions that are the internal region described by material. In this case, we have apnea. And again, this region are described by physical properties. We can have the electric permittivity, thermal conductivity if you want to solve the Fourier equation in your system, then effective mass of the dose effective mass for electron, O's. Then, let's say the most important ones are the effective masses and the permittivity, the band gap, and the electron affinity of your material, and the mobility. Then you can have a lot of our other properties depending on the, say, on the equation that you want to solve and the model that you want to introduce in your system as ferroelectric material, or so in case you want to solve the Ginzburg-Landau equation, or you want to have phase-changing material. Inside the region, they are defined also the defects that you can find therein. In this case, we have a vacancy that is neutral, that is called V0, and they are represented by the balls, the red balls here. We can change the distribution, so their number. I can they will be generated, and maybe we can have a look at the defects. Again, they are defined by physical properties as the capture cross-section, their charge, are they neutral, are they not neutral, then maybe the thermal ionization energy, the relaxation energy associated to them, and we can have also mechanism like the generation mechanism that originate new defects into the device. And in this case, we have the activation energy. What we call activation energy can be represented by the defect formation energy in material modeling. And again, for silicon and other material. Then, once we have a device, we can define a test. Again, a test, we have a list of predefined tests here. It's really small, the character, I apologize. So drain current versus drain gate voltage. We can have transient simulation. We can have capacitance and conductance simulation. We can perform stress simulation and some particular set of operation as the formation of a conductive filament in resistive RAM or CBRAM devices. We can have phase change materials and so on. These are test simulation. So in the, let's say, in the view of material to device workflow, we start from a device with certain material and we want to obtain the characteristics of the device, the electrical characteristics, or we can have parameter extraction. We start, for example, from experimental data, a CV curve, and we want to infer from it some properties that are unknown of the device or of the material. And then there is also the optimization tool that allows you to, starting from a list of certain material, you can change, for example, the oxide in a device and see which is the best one to reach a certain goal. You want a compliance or a certain threshold voltage. You want a switch with two different currents in the on and off states, and so on. So I've shown you why this is the test I've implemented. Here I apply a simple triangular signal to the system, and I launch the simulation, and I can see the result. Here it is the capacitance versus time. We can plot it. We have changed the voltage at the gate. We can plot it versus the gate voltage, and we can obtain a lot of information and characteristic of the device. So why can be the link with a direct link with the material modeling so important? Because for example, in case I want to add a new layer to my geometry, let's say a new oxide into the stack as aluminum oxide, I add it. It is the green one. And I have to put all the data. In this case, the material was already present on our library. Okay. But in case, let's say, I do not know the bandgap of this material, what I can do is that I can launch the IM2D property browser and have a look either in our database through AIDA or passing through Symfony, or I can open some external databases as using the Optimade API. I can maybe have a look. Here you see a list of databases that implement the Optimade API. Let's search in XTAS. I don't know if it's present here. For this formula, no, it's not present. Okay. I can look on other databases and search, look if I can am able to find it somewhere, and then I can get the data, the results. Okay, it seems not to work today. Let's have a look on materials properties. Okay, here it is. We can have filters. For example, here we are. And we have a list of different results. We can open them, we can inspect and get what we need, the properties. Here is the structure, you can view it. There are some data about the structure. You can download it in the CIF format. You can have an enhanced view of the structure using all the capabilities of JMOL. So you can change not only the color, you can perform measurement, measuring the distance between two atoms of your system, and so on. And you can find the data that are present on the database. Here we have the band gap. We can copy and paste and run our simulation. Now, in order to go more into the detail of IM2D Browser, here in Genestra we have integrated not the latest version, and we have fixed some bugs. So I will launch this in the standalone version. You see, here you have the logo and a list of all the partners that contributed to it. The Windows is the same, but now we have new additional buttons that before were integrated into the Genestra UI. So we have the About, with some details about IM2D, about the INTERSECT project, and references to the European fundings. Then we have preferences, where you can not only change the appearance, so the color of your GUI, but you can also define some details of the plugin. For AIDA, you provide the address of your database, so you can connect to different databases with the same browser. You can select which are the properties to be shown when you do a search on your database. In Symfony, again, you provide the address, and also you have a new field that is the user expertise, so the level of knowledge the user has of DFT simulation. A basic user is someone that has small or no knowledge. An advanced user is an expert of DFT simulation. And here, okay, with Optimate, you provide, it's a link to all the servers that implement the Optimate API. I can open a connection to all the databases. Here it's AIDA. If I perform a search without putting any formula, I will get all the structures that are on our database. The same for Symfony. Symfony and AIDA implement the same capabilities. Just to make sure that the connection is on with the server. So I launch a search. As you see, it takes a bit of time. This because we are based on the former version of AIDA that did not implement the query builder yet. So we have to perform a lot of query to our server. Now that we will base it on the new version of AIDA, things will be much, much faster. We will be able to speed up the search a lot. The material projects, let's see, again for aluminum dioxide. In this case, in Optimate, I can open and perform a search. The search can be performed by formula, by element, so I want to get all the data structure that contains, for example, alumina. I can provide the ID. I can open, again, and see here. If you do not see the structure, means that the CIF file is not present into the database. And you can get information about the stress, about not only the position of the atoms, but also some physical properties. Like here we have the enthalpy, the total energy, and the parameters that have been used to compute them. The same for materials project. Let's filter L2 or 3. Let's say I want to choose the system. I can have a look also on Optimate, through Optimate to materials project, and I will show you the difference. Here I want to search by ID. I will look for the same formula, so I will copy the ID. Here it is. As you can see, you may have a different set of data accessing a database through Optimate or directly, as in this case. This because there is a, let's say, a set of properties that are mandatory, that are this one, the definition of the structure. Then each provider is able to implement or not the API to give you information about other properties that are contained. In this case, material properties decided not to expose this kind of data, as the electric info, what they call space group info, elasticity. For example, you have the elasticity tensor, the band structure, the density of state plot, and so on. This is how you can navigate the databases. Let's have a look to our database. You see, it's really poor because we are running on a server. We have only a few CPUs. It's not for production, this server. So we run just a few simulations on a really small system. But in future, we will test it on a cluster, and we will have a larger set of data, and we will do it. So now here you can inspect what we have. We have, for example, AFNIA. You see here we have only the structure. We can open sodium chloride, where we have computed the band gap and the dielectric constant. Here you see that we have 6 values of the band gap, 3 of the dielectric constant. Why this? Because in the case of dielectric constant, they differ one from the other. We have run 3 different simulations on the same structure with different parameters for the DFT simulation. Maybe we have changed the plane waves cutoff or the pseudo potential. So this is what we get. You can get from our system. We have the relaxed structure, the band gap, the band structure, and so on. This is what you can get, and we want to see what is available. If you click here, you see a list of all the workflows that are present. We can upload a file in the CIF format. Maybe I will do it. I have some examples here that I can use. Let's say I want to add silicon carbide to the database. We can monitor what's going on in the task monitor here. So here is the import from CIF. It has completed and finished, and everything was fine. So we go back. Now if we look for silicon carbide, we should see that there is the entry. Okay, it was already present, and we have already computed the band gap in the past and the dielectric function. I think as the last structure, that is this one, is the structure that we have imported now. We open it, and we see that we have our material. So what I can also do is import from the COD database. In this case, I'm queried the formula. For example, if I put silicon, I will get all the system that, all the entry in the database that correspond to the silicon. And in this case, I will get more than 100 structures. So I will not do it for silicon, and I've shown you that you can do it having a direct access to the COD database. And here you have much more filter that you can use to find your element by formula, by ID, and you can select only the one you are interested in. You can inspect them, select, download the CIF file, and import it. I will close some windows. Okay, then we have the workflow that we have implemented to compute material properties. There is what we call the bandgap workflow. In this work chain, you do not compute only the bandgap, but also the band structure to determine it. Then you can have effective mass, relaxed energy, and the relaxed structure. So you get all this data at the same time, running this workflow. Let's see. It seems not to work. Just a second. Yeah. No. Okay. Here we are. Sorry. So how does it work? These are all the parameters that are required to compute the band gap in our system. We need a crystal structure. We can drag and drop it here. And what is required is the precision, so the accuracy that we want in our computation, high precision, low or moderate precision. I can set the precision and launch the computation. This level, as Flaviano has said before, are based on the AIDA protocols. So you can have different level of accuracy, and this is all based on AIDA. And in the task monitor, you can see now it's running, but it will last long, I think, on the server. Then you can compute the dielectric constant, formation energies, dielectric constant. Again, you put only the structure, and you set the precision. Formation energy, instead, is a more complex workflow, and it's not intended for basic user, maybe. Here, you have to put a lot of entries to fill a lot of fields. What you need is the defect structure. Maybe, let's say we have an example on selenium germanium. You are required the structure with the defect, the host structure, that means the supercell without the defect, and the unit cell structure. Here we have the unit cell structure, that is the host structure, the one without any defects. And we have also a defective structure where we have removed, I think, a germanium, yes. And here you can see the missing atoms. The missing atom. Okay, here you have completed, let's say, the information about the structure. Then you have these parameters that you should set, like formation energy, phase model. You have to fill this field, the defect, which kind of defect it is. This is a vacancy, which is the charge of the defect. Here we have put an additional electron while relaxing the structure. So here we have -1. We should provide the position, and so on. These, unfortunately, are quantities that are not available in an automatic way. So people, in this case, should create the structure with the defect, add maybe an additional electron or 2 electrons, and run a relaxation and get the structure, and input the parameters he has used. Here we have also an help, but in this case, we'll have nothing, because all these quantities, you see, we have nothing, because all these quantities depend on the user, are not, let's say, are not standard properties that can have a default value. Now, what I will do is to, still running, Now we'll restart again the UI using another level of expertise with Symfony. This, when you see the symbol, means that if you change the parameters, it is required to restart the application. So just a few seconds, and we will go back to the demonstration. We can open again Symfony. Now you see here we are identified as an advanced user. Let's have a look for silicon carbide again. The task is always running, so we can keep tracking what's going on, even if we close and reopen the GUI. Now, let's say we want to run a bandgap computation. You see, we are exposed to a larger set of parameters that are required in the computation. So the threshold for self-consistency, the Gaussian smearing, we can define the total energy convergence threshold, so the plane wave cutoff, the ionic force convergence threshold, the K-point mesh, and so on. We have a larger set of parameters, and in case, if we select a structure, because we can use the AIDA protocols to identify which are the best option for this parameter, or let's say the recommended one. We ask for the help, and here for each of the parameters that can have a recommended value or a default, you see now you find 3 values, and these correspond to the fast simulation, to the level, to fast simulation, the intermediate simulation, and the precise simulation that take longer time. And you see that some parameters can change or not. These are the recommended ones that you can use or not to define your input, and then you can launch again your simulation. In this way, you have more control on the DFT computation, and maybe you can change some parameters that you think are better than others. And I know for a DFT expert, maybe you want to go much more into the details, but in some cases, you need only to launch a simulation. You do not want to spend too much time. And as you have seen before, I implement a really robust workflow, and you can rely on them. And yeah, I think more or less this is all. I would like to thank you, and thanks again to Flaviano, Matthias, and in particular to my colleagues that worked at the property browser at the GUI, that are Francesco Benedetto and Claudio Rosati.
Okay, thank you. So I don't know if there are any comments or questions.
A beta version of this is now, as you see, available. And is available also for early adopters. So if you are interested, please contact any of us by email or through our website. And thank you very much for making it possible, make it real.
Okay, so with that, we close the session of this morning. Thanks to all the speakers again. So